Hello, in this last video, we're going to look at solving exponential equations with different bases. So unlike before where we could rewrite the bases and solve it by setting the exponents equal to each other, more often than not when we're actually trying to solve these things, they're not going to have the same bases. So we're going to need to take the log or natural log of both sides. So in this first example, there's no way for us to rewrite 5 and 4 as having the same base. So instead, I can take the log of both sides. The exponent will come out, and I'll make sure I put parentheses around that entire exponent. And I'll get the x plus 2 times log 5 equals x times log of 4. And you'll know that there was no way to rewrite these bases the same, because if I move this log over, like I suggested in the last video, and we put that in our calculator, we don't get an integer anymore. This would actually be something like 1.161, something like that. And that's how we're going to solve this. We won't get an exact answer, but we'll get something that's approximately the solution. So once we put that in our calculator, we can go ahead and distribute just like normal. And we can go through all of the motions and solve this. So you can see once we take the log of both sides, you could have put log 5 in your calculator, put log 4 in your calculator, got it to be decimals, and then started from the second line. Or, as I prefer to try to make it as easy as possible, I'll go ahead and stack the logs on top of each other. Divide one side by the log of the other, and then convert. Either of these ways is going to work. But again, from this point, you would know how to solve this equation. So let's look at an equation that would be slightly different. Now, you may be tempted to just jump in, taking the log of both sides, but maybe it would be easier to kind of divide by 20. Now if we take the natural log of both sides, we see we get a much nicer equation. And I was a little tricky this time. I didn't take the log of both sides. I took the natural log of both sides. And I did that because this e is right here. And if I see an e in an exponential equation, I'm going to take the natural log of both sides. And that's because natural log of e is 1. So this actually reduces to natural log of 5 equals 2 times t. And I get this extremely nice and neat answer, which I could have put in my calculator and gotten some decimal for it. Now, don't fret. It wouldn't matter if you took the log of both sides. You would actually get the exact same thing, even if you didn't reduce at the start. Oh. I think I'm jumping ahead of myself here, because there's actually something. I can't pull that 2t out yet. This 2t is not the exponent for the entire thing. So I would have actually ran into a little annoyance at this point, and I would have needed to split this up as log 20 plus log e to the 2t. Before I could pull that 2t to the front. And since I used log and non-natural log, this isn't some property or something that we already know quickly how to do. So this would end up giving us a bunch of nasty decimals, but we could eventually solve for t. So with this question, I wanted to highlight one, sometimes when we say we're going to take the log of both sides, we may want to take the natural log of both sides, since the natural log is a log with a special base, e. The second thing I want to highlight, if I have a number in front of one of these exponents, it'll be best if I reduce first. The easiest way to solve these will be if it's some number, maybe to a power, equals another number to some other power. Now, it could be the case that I can't get it into this nice form, and we would have to do some trickery like this. But for our purposes, there'll normally be some way that we can solve or pre-solve the question so that when we take the natural log or the log of both sides, it comes out much nicer and much cleaner, like here. All right, and that's everything we need to know for solving logs and exponential functions.